calculus. Kind of put everything in perspective of what we're looking at. I'm going to go to the common case slide. There it goes. The second fundamental theorem of calculus basically is informing us how we take the derivative of this thing called an integral defined functions. Like when we see an integral in the problem and we need to take the derivative of it, like how do we do that mathematically? And we have two formulas that we looked at. We talked about having the common case, which was basically you had a number at the bottom and just x up top. And when you did that, it was pretty easy. The derivative canceled out the integral, and we just replaced the t with an x. And that was the common case that we had. The general case was when we didn't have it as kind of simplified. We had more than a number on the bottom and more than just x up top. And the way we took the derivative of an integral defined function, plugged in the top times the derivative of what we plugged in, minus plugging in the bottom times the derivative of what we plugged in. And then towards the end of class, what we had looked at, we talked about just finding the derivative. Zoom out. So we had like this integral defined function, taking the derivative of it. So we looked at it algebraically. And then we moved in, and where we kind of stopped at was looking at it graphically. So I was going to pick up on this slide and then move into what we're talking about today. So again, I can pretty much guarantee you, as long as they do like a normal AP exam that they typically do, one of your free response questions is going to look like this. They're going to give you a crazy looking graph. They will give you some integral defined function, which in this case is g of x. And g of x is defined as the integral of from 1 to x of f of t. So this first slide, what we talked about, and again, this just kind of gets us set up for the rest of the day. Like in 1a, when we wanted to find g of 3, g of 3 means to plug in 3 for x. So that integral turned into the integral from 1 to 3. Well, from 1 to 3, we know how to find that integral because we know that the definite integral just represents area. So I divided up into shapes and found the area. What's probably more important is what we got to on example 2. And in example 2, looking at like 2b and 2c, in 2b, it was asking us to find the g prime of 6. So this is where the second FTC kind of came into play. If g of x is an integral, then that's going to be the common case. You can take the derivative of it, and the derivative of g prime would then just be the same thing as f of x. So if I wanted to find g prime of 6, g prime of 6 is really the same thing as f of 6, and we made it out of 6th grade math. We know how to find f of 6 on the graph. Then likewise, if g prime of x is f of x, g double prime would be the same thing as f prime. So it's kind of like a lagging kind of thing that we see. G double prime of 6 is the same thing as f prime of 6, which is just a slope, and we can find that from the graph. So to just kind of continue, I just kind of chose a bunch of questions because we want to be able to kind of like analyze this function in the context of like calculus, in the context of the second fundamental theorem of calculus. So this is where I wanted to start at today, problem number 3. And in problem 3, so I left it at the same graph. This is the graph of g of x. G of x is still an integral starting at 1. So if I start finding any area, like 1 is going to be my starting point. And so yeah, so question number 3. Find the zeros of g. In math, if I told you to find the zeros of a function, what's another word you could have used instead of finding the zeros of a function? That's the x-intercepts. So again, we're ignoring all the new stuff right now. Let's kind of think about what we know in math already. If I told you to find the x-intercepts of any function, how would you do that algebraically? Well, we said y equals to 0. So we basically set the function equal to 0. So when I see this, find the zeros of g, what does that mean? That means that basically we're going to take g of x and set it equal to 0. So again, we're just going to take stuff that we already know and now apply it to this integral defined function. So if I want to set g of x equal to 0, well, what is g of x equal to? G of x is equal to this integral from 1 to x of f of t dt. And again, I'm setting g of x equal to 0. So looking at the graph, we want to kind of figure out when this integral is going to be equal to 0. There should be a really obvious and easy one we can find. What's one x value we know for certain is going to have an integral that's equal to 0? 1. So 1 should be the obvious one. Why is that an obvious one? If you start at 1 and end at 1, you haven't gone anywhere, you haven't accumulated any area, so we know that the integral would be equal to 0. When this integral is 0, that's the same thing as saying g of x is 0. So that is literally an x-intercept on the graph of g. Again, we are looking at the graph of f. Then we want to talk about finding another x-intercept, or possibly seeing if there's any more x-intercepts. What would it mean if this integral was going to be equal to 0 again? How would that happen on this graph?
The net area is 0.
The net area would be 0. So basically, just want to kind of go across this graph and see, like, I can clearly see it starting off with some positive area. And then I want to see if there's going to be some negative area that will cancel it out so that we get to 0. I'm going to pause with me. My marker's not changing colors, and I like to use different colors. So I'm going to restart OneNote, and then we'll pick back up. Let's see if that worked. All right, so we do want to go ahead and look at that graph. Those of you at home, I'm just resharing it. There we go. So we do want to go ahead and see when that net area is going to be 0 again. This integral, remember, is starting at 1. That's important to look at. So starting at 1, again, I can just divide it into shapes that we know. So again, we have like 4. This is an area of 2, area of 1. Another triangle, 1/2 base times height. That's an area of 2. Overall, that positive area is like what, 4, 6, 7, 8, 9. Area of positive 9. The net area is going to become 0 if we reach negative 9 somewhere past that. So again, just going to kind of keep going along. Here's a triangle, negative 1, square, area of negative 4. Another triangle of a negative 1. So that is putting us at negative 6. We've almost canceled out all the area. Continuing, negative 1, negative 2, there's negative 3. So that positive 9 is going to be canceled out completely by negative 6 and 3. So I know that the integral is also equal to 0 at x is equal to 10. If the integral is equal to 0 at 10, then g of x has x-intercepts at 10 as well. Don't make the mistake and think the x-intercepts are where f is having an x-intercept, because again, this is the graph of f. G is literally the integral of the graph that we're looking at. So we kind of had to use the integral to answer that question. Anything I can make a little bit more clear or explain a little better about that question?
Did you start at 4 just because there was like a change in like, because it hit 0 essentially?
Yeah, so I like did the from 1 to 4 just because that was where it was like all positive, and so it switched at 4. So I knew basically I wanted to find all that positive area first, then to figure out what would cancel out from it. And I didn't like continue, like of course there could be more than 2 x-intercepts, but if I'm looking at this graph, the rest of it is negative, so there's not going to be another chance for it to be like positive and then negative to cancel back out. So this one would just have 2 x-intercepts at 0, excuse me, at 1 and 10. Next question, we are going to see a lot of things from first semester kind of in this topic, like we are doing like a lot of derivatives. That's kind of what the second FTC relies on. So looking at this one, same graph, same g of x. And I want to find the absolute minimum value of g. I am going to have to do a little bit more specific on this one. So like I'm going to go ahead and say heads up, people who did not have me first semester, you did not learn how to find absolute extrema. So I'm going to do like a little mini lesson for y'all. Probably some of you had me last semester, needs the review anyways. But we want to talk about finding the absolute minimum of g. So again, let's kind of put a frame on this. We're looking at f. G is the integral of that one. So in some ways, we're looking for like, what's the lowest possible area we're going to have on this graph. And this one I think is easy to kind of figure out and kind of guess where that minimum area would occur at. Again, if you're starting at 1, But let's just review the calculus of how we do absolute extrema, / for those of you who didn't have me first semester, let's kind of review that. I'm just going to kind of add a blank page, and let's do a quick mini lesson. So if we need to find an absolute minimum or an absolute maximum, I'm going to compare that to finding a relative minimum or a relative maximum, which everyone who, even if you didn't have me first semester, you did learn relative minimums and relative maximums. So let's just kind of talk about those first and kind of compare and contrast them. When doing relative minimums algebraically, think about the process you had to go through. The first thing you had to do is basically find the first derivative. After you found the first derivative, you wanted to find when that first derivative was equal to 0 or when that first derivative was undefined. That was going to give you what we call our critical points. Once we had those critical points, what did we create in order to determine whether we had a relative minimum or relative maximum? Sign chart. So we did a sign chart, and then with that sign chart, we basically looked for sign changes in the derivative. Like we know if the derivative changed from positive to negative, that would be a maximum. If the derivative changed from negative to positive, that would be a minimum. I'm going to compare that to absolute minimums and absolute maximums. I will say in AP Calculus, we always will find an absolute minimum or maximum over an interval. So it never will be over the entire function. It'll be like a clear starting value and a clear ending value. The steps for everyone, so I guess either reviewing or brand new, starts off the same. You're still going to find the critical points. You are still going to find when f prime of x is equal to 0 or undefined. But instead of making a sign chart, we do a candidates test. And so let's talk about what a candidates test is. When I say a relative minimum or a relative maximum, that's just like a high point on the graph or a low point on the graph. It may not be the lowest, it may not be the highest, it's just low, kind of around where it's at. It's a turning point on the graph. When I say absolute minimum or absolute maximum, we want to find the highest y value, basically, or the lowest y value. So we don't want a sign chart. The sign chart just tells you where it changes direction at. What we call a candidates test will tell us the highest value or the lowest value. What goes on a candidates test is basically a t-chart. So we're not going to overcomplicate it. It's just a t-chart. Plug in x coordinates, get out a y coordinate. What goes on your candidates test is going to be those critical points, which again is coming from when that first derivative is equal to 0 or undefined. Those of you who had me last semester, what else also has to be included on your candidates test? So we do plug it into the original equation. What other x values do we have to include? The endpoints. It's been a while, but we remember we have to find the endpoints. And basically it's like a t-chart, and you'll have your x values and you're plugging it into the original function. The critical points and endpoints are going to be in your x values, and you're going to plug it into the original function, and then just visually look for like the highest value, and then visually look for the lowest value. Not going to spend too much time on it right now because it won't happen in this unit. There were cases where we tossed out an answer because it was on an endpoint that wasn't included, but in this unit, the endpoints will always be included, so I'm not going to worry about that for right now. But that's what we're going to create to find an absolute minimum or an absolute maximum. And so yeah, let's just go ahead and jump back to the example. All right, game back in. Timeout is over. Let's go ahead and find the absolute minimum value of g. So again, when you're in my class and you're in calculus, you look to see anything talking about an absolute minimum or maximum, just know you're going to create a t-chart. So I'm going to go ahead and just draw in my t-chart. What goes on my t-chart is x values, and we want to find it in the original function. And I'm looking for an absolute minimum of g. So I am going to plug everything into g of x. So now we need to remind ourselves what goes always on our candidates test. The first thing that will always go on your candidates test are going to be the endpoints. Looking at this graph, what are the endpoints that we see? 0 and 12. I like putting brackets on that just to kind of show me that those are the endpoints, but like we're basically going from 0 to 12. And then what goes between those numbers is going to be our critical points. So let's remind ourselves in calculus, how do we find those critical points? Those critical points are coming from when the derivative is equal to 0 or undefined. Thankfully for these problems, we don't need to really worry about when the derivative is undefined. That's going to be when the derivative is equal to 0. So we're basically looking for when g prime is equal to 0. Well, using the second FTC, what is g prime the equivalent of? F of x, right? So remember, g of x is the integral. G prime is equal to just f of x. That's using the common case. So I'm basically looking for where g prime is equal to 0, but g prime is equal to f. So I'm basically looking for when f is equal to 0. Well, where is f equal to 0 on that graph? At 0, 4, and 8. So those are my critical points. 0 is already an endpoint, so I'm not going to repeat it, but we do have 4 and 8 to add to it. If I'm grading this on your quiz, even if this is graded on an AP exam, there will be 2 points here that you will get points for. You would have points for considering the endpoints, and then points for considering the critical points. So at least we've earned a bunch of points just by showing that. Now we want to plug it into the original function. This is where we want to be careful at. What is g of x? G of x is the integral. And this is where it gets a little bit tedious. I want to see potentially 0 could be the highest x, y value, or it could give me the lowest y value. So I need to find the integral, and again, it's from 1 to 0 of this function. I want to find the y value at 4. How do I find the y value at 4? Plug it into the function. So it's going to be the integral from 1 to 4 of f of t dt. How do I find the integral, or excuse me, how do I find the x value at 8? That's going to be the integral from 1 to 8 of f of t dt. And then we want to find the integral from 1 to 12 of f of t dt. Then once we find one of those values will be the lowest one, and that's going to be the absolute minimum. If it was the absolute maximum, one of those numbers is going to be the highest value, and it would be my absolute maximum. So let's go ahead and find my integrals. Again, this integral is starting at 1. So that first one, you are going from 1 to 0. That is backwards. That triangle has an area of 1. But since we're going backwards, what are we going to say the integral from 1 to 0 is? Negative 1. From 1 to 4, again, we kind of already did this on the other slide, but we had 4, 1, 2, and 2. 6, 7, 8, 9. The integral from 1 to 4 is 9. What's the integral from 1 to 8? Well, it's going to be that 9 minus this negative area. So minus 1, minus 4, minus 1. Subtracting 6 from that. So g of 8 would be 3. And then what is g of 12? Keep subtracting. So right now we're at a net area of 3. Minus 1, minus 6. So minus 7 gives you negative 4. So again, what have we found? Yes, we have evaluated definite integral. But again, g of x is a definite integral. So the value of the definite integral is basically the y value of g at each of those x coordinates. So now we can go ahead and kind of answer the question. The question asked me to find the absolute minimum. Well, what is the lowest y value I see? Negative 4. So then my answer would be the absolute minimum is negative 4.
Did you say it's at?
You could add there, it is at x is equal to 12. Do want to be careful, it does say find the absolute minimum, so it is looking for the y value. And then before I take questions, didn't ask us for the absolute maximum, but we can still answer it. What is the absolute maximum on this graph? 9. So that's the highest value we see. The absolute maximum is 9, and it occurs at x is equal to 4. I think when you look at that graph, you could probably have figured those out without the candidates test. But again, you do need to kind of show that candidates test as your justification. The max, I think, is pretty easy to see. That's where the positive area stops at. So anytime you go past 4, like your area is never going to get bigger. It's always going to be subtracting all the way to the end of the graph. I think it also makes sense that the minimum is at 12, because that would include all possible negative area on that graph. So that's how we do a candidates test. We use that for absolute extrema. Always include your endpoints and your critical points. And again, where the points would come from, if this was on your quiz, it's probably on your quiz, I would give you a point for considering the endpoints, a point for considering the critical points, and then a point for the answer. Questions on that or things I can clarify? Yes, Lily?
So do we have to like justify it and say see candidates test?
So you don't have to justify it, like it will be phrased, like show the work that leads to your answer,
Okay.
but just like showing it will be enough.
Okay.
Any other questions on that one? All right, let's go ahead and keep trucking along. Examples 5 and 6. Same graph, just more questions. Number 5, on what intervals is G increasing, and then justify your answer. So let's talk about this one. This one kind of harkens back to some stuff that we did back in Unit 3, where we had to kind of look at the graph and justify when a function was increasing or decreasing, or when it was like concave up or concave down. We were looking at the graph of the derivative or something like that. So let's talk about what we need to make sure we do when we justify our answer. In calculus, to earn credit, when justifying your answer, you do want to make sure your answer is clear. So you're not going to say things like it. You're not going to say things like the slope. Like you're going to be clear. So you're going to say things like f prime. You're going to say g prime, the derivative of g. We're not going to be vague and just say things generically like the slope or it. We do also want to make sure we are concise. Please save the essays for English class. Just like say the answer, because, and your reason. In fact, I often see when students try to get too wordy, they start putting in like wrong information. So just leave it short and sweet. And then clearly you want to make sure that it is correct. In terms of being correct, on the AP exam and for my class, what makes it correct, in addition to the calculus being correct, is you must refer to the given graph. And what do I mean by refer to the given graph? Every single answer we provide is going to have to mention f. Like we can't talk about f prime, we can't talk about f double prime, we can't even just talk about g. We're going to have to talk about f somewhere in our answer. So let's do number 5. Number 5, it says on what interval is g increasing? I like doing the justification first, it just helps me form my answer a little bit better. So I'm going to go ahead and just put the because part down. Because in calculus, how will we know that the graph of g would be increasing? So we know that will be increasing if the derivative, right, g prime is positive. But I can't just say because g prime is positive, because I don't have the graph of g prime in front of me. But we do know what g prime is equivalent to. What is, again, g prime equivalent to? F of x. So how can we just make that part of our answer? Just sneak in a little, g prime is equal to f. So we know it will be increasing because g prime, which is equal to f, is positive. And then now we can just kind of read the graph. And what interval is f positive? And positive would just mean like above the x-axis, correct? From 0 to 4. And that's all I want to see for that answer. Don't try to explain it and get wordy. interval because, and then reason.
Do you want brackets or?
The intervals will always have parentheses and not brackets. Questions on that? All right, let's do number 6 then. Number 6 says, on what interval is G concave up? I like doing my justification first. What would we know kind of calculus-wise that's going to make G concave up?
G prime.
And there's 2 options we can say. So I'm going to write both of them and we'll kind of pick the one that is correct. What's one way we can prove that something is concave up? G double prime is positive. So that could be one reason, because G double prime is positive. Or because G prime is increasing. Typically, when we think about concavity, I know we often think about the second derivative. Yes, when the second derivative is positive, that does mean the graph will be concave up. But a graph is also concave up if the derivative, the first derivative, is increasing. Let's say what these are equivalent to. We already said this one. G prime is the same thing as F. What was G double prime the same thing as then? F prime. If I want to receive full credit on the AP exam, which justification is going to earn you credit? The bottom one. You have to refer to the given graph. Is that one correct? Technically, yes, but you're not using the given information. So we're going to use the second option. That's the one that's going to give us credit on the AP exam and on our quiz and on our test. Well, when is G prime increasing? G prime is increasing when F is increasing. When is F increasing? It's increasing from 0 to 2 and then 7 to 8. So I have 0 to 2 and then 7 to 8. Question on either of those 2 questions. All right, last slide we're doing today. Same graph, same g of x, more questions kind of analyzing it. It says at what x coordinate within 0 to 12, so we're not including 0 or 12, does g have a horizontal tangent line? So again, pulling stuff from our heads from first semester, when we see a function having a horizontal tangent line, what calculus fact should we be thinking about or connecting to that statement? The first derivative is equal to 0. So when we see horizontal tangent line, what does that mean? That means the first derivative is equal to 0. I don't know what the graph of g prime looks like, but again, what do we know that g prime is the same thing as? F. Again, that's coming from the derivative of an integral. G prime is the same thing as f. So if I'm looking at where g prime is equal to 0, I'm basically looking at when f is equal to 0. Where is f equal to 0 within the interval from 0 to 12? F is equal to 0 at 4 and 8. I know that's where I have horizontal tangents on g because that's where g prime is equal to f, which is equal to 0. And then kind of the follow-up question, this one's kind of connected to it. We have, where that came from. At each x coordinate found in the previous question, so at x is equal to 4 and x is equal to 8, state whether g has a relative minimum, a relative maximum, or neither. So we have 2 possible horizontal tangents. We have a possible horizontal tangent, or not possible, it is a horizontal tangent, at x is equal to 4. And we also had another one at x was equal to 8. Kind of already discussed this when I did like the mini lesson on absolute extremum. How would we know the graph is going to have a relative minimum or a maximum? What are we looking at when we're determining it has a relative minimum or a relative maximum? Sign changes. So again, when we see this in this class, big thing we're looking at is going to be a sign change. A sign change specifically in what? G prime, or G double prime? G prime, right? So if it goes from increasing to decreasing, it'll be a sign change in G prime. What have we been saying in this problem? G prime is equal to F. So basically, we're looking for sign changes in F because that would be the same thing as saying sign changes in G prime. So let's talk about 4 first. I'm going to scroll back up to the graph. At 4, here it is. What is the sign of F changing from and to, or is it changing at all?
Positive to negative.
Positive to negative. F is above the axis and positive, then F is below the axis and negative. We just said that G prime is the same thing as F. So if F is going from positive to negative, G prime is also going from positive to negative. If your derivative switches from positive to negative, are we having a relative minimum or a relative maximum? Positive to negative will be a maximum. So x equals 4 is a relative maximum. How do I know that? Because, let me do proper grammar, don't need a comma there. Because G prime, which is equal to f of x, changes from positive to negative. Again, what all do I need to include in my answer? I needed to say it was a relative maximum. I needed to refer to the given graph, so G prime is equal to f. How did I know it was a relative maximum? Because it changed from positive to negative. Let's now do the same thing for x is equal to 8. There it is there. G prime is the same thing as f of x. What is f changing from and to at 8? It's not. It is negative. And then after 8, it is still negative. Well, if f is negative to negative, then G prime would also be from negative to negative. So it's basically always decreasing along that interval. So is x equal to 8 anything special? No. So x equals 8 is neither. Why is it neither? Because the derivative, which is the same as f, doesn't change signs. Questions or things I can clarify on that? Yes, Mitch.
So back to 7.
Mm-hmm.
So it says it's between 0 and 12. Why isn't 0 one of the x values?
I didn't include 0, I made the interval this way because in calculus we never talk about relative extrema on the endpoints. Because we were talking about where it changes, like if it's an endpoint, you don't know what it's doing, like there's nothing before it, so you can't talk about it changing signs. So I just didn't include it for those.
So if 12 were at 0, then you wouldn't include that?
I wouldn't include it either.
Okay.
For a relative. For an absolute, then yes I would, because it would go on at candidate's desk. Any other questions or things that I can kind of clarify? All right, so that's where I'm going to stop today's notes at. Same exact checklist that you saw yesterday. So at this point, you can finish all of homework 1, that second FTC. Please don't neglect it. Like it is divided into kind of 2 parts. The first half of the homework is very algebra based. The second half is more of the graph ones that we saw. Speak to me if you do need to talk about recovery on the Unit 6 test or anything like that, so we can work things out there. Some things I do want to kind of get you prepped for next week in this class. We are starting the first fundamental theorem calculus word problem. Just like throwing it out there, this is going to be a topic that most students tend to find one of the more difficult ones that we see in the semester. Some heavy notes today that we were doing. Like Monday we'll be taking notes, but like the meat of the topic is really going to be on like Tuesday and Thursday. So like those are going to be really days we just want to kind of show up, ready to soak up as much as you can. Homework 2, when we get there, it's a beast. It's a long homework assignment. So next week, definitely just know you can't procrastinate on the homework. And also for next week, this topic, a lot of it is going to be calculator required. as in you will not be able to do the calculus without a graphing calculator. So just make sure you have one available. If you're at home and don't have one, I need to know that like today, so I can get you one, but you will need a graphing calculator to do the calculus that we're doing next week for most of the problems. The time is, what is it, 3:10, so you do have about 20 minutes to kind of continue working on homework. I would recommend trying to knock out as much of homework 1 as you can, just so you can really focus next week on homework 2 and not have any other homework kind of hanging over your head. So y'all can go ahead and get started with that. If you're at home and want to hang back and ask any questions,